Hi, and welcome once again to Thermal Live. I'm Jennifer Arroyo, Editorial Director for Electronics Cooling. Thank you for joining us, and I hope that you've been enjoying the program so far over the last 2 days. For our next presentation, you'll be hearing from Joseph Petri, an Electronic Assembly Solutions Account Manager at 3M. Joseph has spent over 30 years in the industry and previously managed a 3M industrial adhesive and tape business. At the same time, he was working to drive innovative solutions with customers as an application development manager and key account manager. In this session, you'll see that experience in action as he outlines thermal management solutions for automotive and mil-aero as connected devices continue to demand greater functionality. Take note of the Q&A box on your presentation screen. You can submit a question at any time for Joseph to address at the end. Thank you for joining us today, Joseph.
Good afternoon, everyone, and welcome to the Thermal Live Experience. My name is Joseph Petri from the 3M Electronic Materials Solutions Division. My short presentation today is to talk about the Internet of Things and the increasingly powerful connected devices that surround us in our day-to-day lives. Design engineers that are online and participating in this event are now dealing with new serious challenges as these powerful devices are generating more heat. Today's short presentation is going to talk about some of our device trends and why thermal management solutions are important in improving the reliability of devices. We'll talk a little bit about how our thermal interface materials work, some applications, and the specific product selection criteria that comes into play when making those critical product selection decisions. We'll spend a couple minutes talking about specific market segments and some applications and products that were selected in those applications. And then we'll finish with a few application profiles on specific products. So thank you for participating, and let's dive right in. There are trends that are driving the need for thermal interface solutions in the electronics marketplace. The first is data consumption. As devices get more powerful to handle the amount of data that is being transferred over our IP networks, they are generating more heat. We've all heard of terabytes, gigabytes, megabytes. What about exabytes? A friend of mine, Larry, thinks the next one will be yottabytes. These powerful devices and the data that's traveling across our IP networks are generating heat that can be managed through thermal interface solutions. A second trend would be connected devices. Look around inside your car and the number of connected devices that are there within your new vehicle. The Internet of Things is expected to continue, and these machine-to-machine interfaces will be a great part of the amount of data that's being transmitted over our networks. Another trend is the ongoing use of circuit boards, flexible printed circuit boards, or electric vehicle batteries are going to drive the need for additional thermal interface solutions. So it's clear to see that those trends in electronics are driving opportunities for thermal management. As the devices get more powerful, they're generating heat. In fact, heat is the #1 cause of failure in 55% of the occurrences, according to the BCC research from 2019. And the participants that are here on the call here at Thermal Live today know this, and the work that you're doing is quite important to help dissipate that heat and increase the reliability of your device. I now know the importance of thermal management for the reliability of electronic devices, but that wasn't always the case. Years ago, I found myself on a Saturday sitting in front of the TV watching college football. I was working feverishly on my laptop computer because my projects were due on Monday. I was making some great progress. But I did start to feel the heat. I felt the heat on my laptop. I did notice the fan working a little bit harder than it normally did. I couldn't quite notice when the program started to slow, but I quickly found out and knew how bad the situation was when my computer completely shut down before I was able to save any of my work. So we all have experiences, perhaps with thermal issues and electronic devices, but think about what could happen and the potential outcomes that could occur in important markets such as automotive or aerospace and defense. Devices within those markets, if they were to overheat and just suddenly shut down, would have devastating impact on everyone. I think that old laptop of mine could have used a better thermal interface material. A thermal interface material is any kind of material that can be inserted between components in order to enhance the thermal coupling between them. For example, an electric vehicle has a battery pack that might be generating some heat that it would be dissipated by placing a thermal interface material between the battery and a cooling plate that will help keep it in its operational temperature range. My old laptop probably could have used a new thermal interface material between the processor and one of the heat sinks that the cooling fan was trying to run air across. There's many solutions that can be used here as this interface to enhance that thermal coupling. Thermal pastes, thermal adhesives, thermal gap fillers, sometimes known as gap pads, thermally conductive tapes, and thermally conductive epoxies. What we all work toward is moving heat to increase the reliability of that device. And that's the purpose of a thermal interface material. However, what's critically important in the movement of that heat is how the thermal interface solution has a form-fitting contact between the substrates. You got to get the air out. So for example, let's say we have a heat source and we have a cooling plate. Our goal is to move that heat across that distance. Many of you, or all of you, are probably familiar with Fourier's law, and this is a variation of that original formula, that old science. We want to move that heat Q from one hot side to the other. By selecting a material with a given thermal conductivity that can then be placed between those two substrates. In the diagram there, you can see we've inserted perhaps a gap pad, or gap filler, or even a thermally conductive tape. And you measure the temperature difference across that gap you're trying to move, and then take into account the area of material and the thickness of that gap to measure the heat flow in the formula. Now, these two substrates, the heat source or cooling plate, are not necessarily smooth. And it's that form fitting and how well the material fills in and removes air pockets that increases the performance and reliability of the device by having the best thermally conductive solution. An example of removing the air could be by filling that with a soft Shore 00 gap pad, Shore rating of 5 to 15, to remove and fill those air pockets. Softer thermal interface materials have that gap filling property and ability to have the most efficient movement of that heat within the device. But unlike a mathematical equation such as Fourier's law, selecting the right thermal interface material is a lot like art. You've got to think about a given application's specific requirements to find the best form, fit, and function that will drive the best solution. It's not just selecting the best K value. There's a lot of factors that can come into play. Think about application requirements such as gap thickness, electrical interference, maybe industry requirements, maybe the substrates themselves. There are a lot of product features and solutions that can come into play to address each one. For example, there could be an industry requirement for UL ratings for flammability, for outgassing, such as the use of acrylic thermal gap pad chemistry over traditional silicone gap pad chemistry to reduce dramatically the amount of siloxane present in a thermal gap pad assembly. There could be the need for certain levels of dielectric strength. There could be thermally conductive tapes that provide very good dielectric that exceed the requirements needed of traditional polyester films. Gap thickness. There are custom gaps that need to be filled, and having the ability to make custom thicknesses of filler materials is a keen advantage when we're trying to select materials that are form-fitting and removing those air pockets. There could be specific needs due to the roughness of the materials, the heat source and the heat sink, that require dramatically lower Shore double zero softness, so the material itself wets out better under lower compression. There could be issues in assembly, in your assembly process itself. For example, there are acrylic gap pad materials available in roll formats for high volume rotary converting. This allows for lower costs during final assembly in that the materials can be robotically applied, making it much easier to handle and use in the final assembly processes. So I do wish there were more go-to materials that we could just recommend for a given application, but time really should be spent to understand the application requirements to drive the best solution for a given application. So let's just take a moment here and talk about specific application requirements that drove a customer to a specific thermal solution. There are many market segments for thermal interface solutions, but I was going to highlight two markets where 3M Electronic Materials Solutions Divisions provides a wide range of product solutions. We'll focus on thermal interface solutions here today, but in the automotive market, one of the key drivers in the hybrid electric vehicle and electric vehicle is lightweighting. That's an application requirement that they do bring up, and we have acrylic chemistry that is significantly lighter weight than traditional silicone chemistries to help in the battery pack, battery module assembly. There are other needs for thermal interface materials, LED lighting, for example, GCUs, ECUs, and other modules within the vehicle. Think about the aerospace and defense market. There are many applications that are similar in the automotive market, but they have perhaps differing requirements for their marketplace, such as products that could be used within the cockpit. Perhaps the need in an aerospace or defense cockpit application is very low outgassing. So once again, if you could have eliminate the siloxane outgassing within the cockpit area of the thermal interface materials that you're using, That would be a key benefit and a driving interest to design engineers in that marketplace. For the automotive marketplace, electric vehicles have moved to using thermal interface materials to keep those battery packs running cool. The original designs basically had no battery cooling, and they made some improvements and moved to air cooling. Many of the electric vehicles of today utilize liquid cooling, and it's this interface between the heat-generating battery pack and the cooling heat sink cooling plate is where you'll find thermal interface materials coupling those two surfaces to help keep the vehicle running at an optimal temperature. These drivetrains are very energy efficient. However, they only lose 25% of their energy lost as heat as compared to internal combustion engines, which lose almost 80% of their energy to heat. However, this heat still needs to be dissipated, and so by coupling those two, battery pack and cooling plates, with a thermal interface material, we successfully extended the battery life and driving range of these electronic vehicles. We spoke earlier about providing examples of thermal interface applications. Here, we have an electric vehicle battery pack. Critically important is to keep the battery pack within a temperature range to ensure long battery life and an expected vehicle driving range. To make that happen, the proper thermal gap pad needs to be selected that provides the best form, fit, and function between the heat source, which is the battery itself, and the heat sink, a liquid cold plate cooling system that keeps the battery cool. In this example, an OEM could select 3M's 5571 acrylic gap pad. First, their thermal requirements can be satisfied with the 3M 5571's high thermal conductivity at 2 watts per meter Kelvin. This gap pad material can move the heat and meet their cooling requirements. Second, an OEM can select the appropriate caliper of the gap pad material based on the material's softness or shore value. Here, an OEM could select a 1.5 millimeter thermal gap pad and with minimal pressure compress it to achieve their targeted thermal conductivity. There are applications where a design may have selected a very thick gap pad and were instructed to greatly compress the material with mechanical fasteners to achieve the thermal performance. It's better to match the actual gap thickness, pressure, and a material's shore value for the best form, fit, and function, and do not overstuff. Another important selection criteria is assembly. Will this part be hand applied or maybe machine applied? Here, 3M 5571 is supplied in a roll format, which allows for high-speed rotary converting and lower converting costs. Always be sure to understand industry requirements or trends. In automotive, lightweighting the vehicle is always part of a design, which is intended to extend the driving range on a single charge. The 3M acrylic gap pad 5571 are actually 20% lighter weight than an equivalent silicone option. Thermal runaway is also an industry requirement and is in concern. So selecting materials like 3M's 5571 that have a UL V94 V0 rating for flammability would also be important for an electric vehicle battery pack assembly. The second example I'd like to give you here in the automotive marketplace surrounds an electronic control unit, ECU or TCU. This this device is now controlling a broader number of complex functions within the vehicle, and there's a dramatic shift of power which introduces additional design challenges, and you got it once again, thermal management. So in these types of applications, we've got to think about things like what's the gap, how much heat are we trying to move, but also assembly. In this particular case, I've got examples here of two different types of assembly. The first assembly will end up having that printed circuit board assembled inside the case, but then actually held in place with mechanical fasteners, perhaps screws, some clips, even an epoxy, or it's formed in place and held in place. However, there are some applications where the thermally conductive tape not only has to move the heat, but it needs to provide high adhesion. The tape itself is going to hold the board into the module to help move the heat to its surrounding case. In this particular case, how do you choose, right? Well, you could use a product that has good compression, a softer material that can be compressed, such as 3M's Gap Pad 5590, 2.8 watt per meter Kelvin in an acrylic chemistry. They could also choose, because the case might be not as smooth, a more conformable version of that same product. 3M's 5550, while having a 3 watt per meter Kelvin and V0 rating, it actually comes in with a Shore value of Shore 0030. It makes it almost gel-like and able to wet out and remove those air pockets under limited pressure. The last example is one of our thermally conductive tapes. 3M 8711 comes in a variety of calibers, but it also provides very high adhesion. Many of you are familiar with 3M's VHB, and 8711 almost feels like a VHB in its ability to have high holding power and wet out on surfaces while still conducting the heat adequately for a given design. So in this case, assembly requirements also come into place when selecting the best form, fit, and function. Automotive LED lighting is another area where thermal management is critically important. LED lighting is found in our vehicles, but it's also found all around us, in all the devices, and in our homes. And moving that heat away from the board, which contains the light, will increase that light output and that board life, and improving overall quality. Here, they're attaching that LED base to some sort of heat sink, which could be the housing of the tail light or a heat sink within that cavity. So they need something that has high adhesion. Here, people select 3M's 8926 with a 1.5 watt per meter Kelvin in a pressure-sensitive tape format. 8926 has got very easy handling, can be rotary die cut for high volume applications. Its high holding power and V0 rating provide an excellent solution for LED lighting. Whether found in the seat back on the next plane that you're able to fly or in the back seat of a car for the automotive market, TVs or displays also have needs for transferring that heat and keeping that device running cool to improve the reliability and life of a display. You know, many of you guys might be familiar with the viscoelastic properties of VHB, but this is a good example of where they will utilize one of our very thin thermally conductive tapes that has high adhesion on copper or aluminum, but because of that viscoelastic property, provides very high strength in a very thin thermally conductive tape. We have solutions as thin as 2 mils in products such as 9882, or in this case, our 8805 and 8810 thermally conductive tape, highly conformable, high adhesion, great options for thin devices with thermal requirements. There are many applications for 3M products in this photo. In addition to thermal applications, 3M products can reduce glare, improve wireless communication, reduce electromagnetic interference, making multifunction displays, GPS systems, and in-flight avionics systems more reliable. For thermal applications, important selection criteria would not only be the thermal conductivity of a tape to keep systems running cool, but products that are thin and do not outgas, causing display issues within this confined space. 3M thermal gap pads such as 5590 or an even softer version, 5550H, would be excellent candidates for these avionic systems. For thinner assemblies, 3M high adhesion thermal tape 8810 provides the thermal conductivity needed for the systems, but also has a very high bond strength for attaching heat sinks in confined spaces that don't have the space luxury of clips or other mechanical fasteners. In both cases, design engineers should consider industry requirements and select materials that eliminate siloxane or silicone. This siloxane gas can build up on adjacent electronics and over time negatively affect system performance. Siloxane can also affect displays and pilot vision by leaving a cloudy film on displays surfaces. 3M has an extensive portfolio of acrylic-based thermal solutions that do not outgas siloxane and are a preferred candidate for confined spaces found in aircraft. To summarize what we discussed today, I'd first, though, like to start off by saying thank you. Thank you for taking the time to attend Thermal Live 2020. Some great speakers participating in this event, and some great interaction and questions were coming up during our call here today. Today you learned a little bit about electronic trends that are driving thermal opportunities and thermal solutions. You learned a little bit about how thermal materials work, how to move the heat, a little review of Fourier's old science and law, but you learned about new ideas and how specific markets have application requirements and some of the selection criteria that comes into play to select the best form, fit, and function. And in conclusion, I kind of finished with giving specific application examples and product solutions. Don't think that those are just for aerospace or automotive, but are likely relevant to the thermal projects that you are working on with your electronic devices. Let's answer a few questions that were submitted by the audience.
Okay, audience, please continue to get in those questions. We'll get started with our first question. What is the number one issue you see when trying to determine a thermal management solution?
Well, thank you very much for that question. Hey, what I'm seeing quite often is we are being contacted to say, what do you have that can replace or is equivalent to this? And what we commonly start to do is go and review the application requirements again. Quite often I find out that an application may have been using a gap pad that is much thicker or overstuffed as compared to what their target gap pad thicknesses could have been. And as we review the application, we could many times move to 1 millimeter or even 0.75 millimeter gap pads, when in the past they may have been using something much thicker. Thanks.
Okay, great. Our next question is, what is the max temperature 3M acrylic pads go to?
That's very important for sure. We've got this extensive portfolio of gap pads, thermal tapes, thermal epoxies, and one thing that 3M is constantly doing is trying to continue to innovate. Customer input drives innovation. And in one area, we have been putting a lot of attention and focuses in that acrylic gap pad portfolio. We have now created and are offering the marketplace acrylic gap pads that are able to withstand 130 C continuous temperatures. And in many electronics application, this is very attractive for higher temperature applications that in the past had only been able to be fulfilled with our silicone portfolio. So 130 C continuous.
Okay, thank you. Our next question, why would you use a thermal interface pad instead of thermal interface tape?
Okay. Yeah, there was some examples in the slide deck that talked about the requirements of the assembly. And in some assemblies where they are needing thinner and thinner thermally conductive materials, we could lean toward our thermally conductive tape products such as like 8926, 8805, down to 0.2 millimeters, provide not only the conductivity, but they provide the high adhesion in that assembly where they may not have the room or space for their traditional heat sink there to be mounted, for example. So in applications where the assembly itself is relying on the tape for the final assembly, you go with a high adhesion 3M thermally conductive tape.
Okay, we have another question here. What are other thermal management applications for electric vehicles?
Yeah, we have had a slide that we've shared in the past that kind of blew apart one of those rolling computers in an electric vehicle. And when you look inside the vehicle itself, there are many different applications. The battery is the common one people definitely are aware of, but there are thermal applications related to the charging system, either in or outside the vehicle. There are motors that need to operate at continuously cooler temperatures where thermal tapes are applied into areas around motors. There are sensors within the vehicle, and even the human interface systems, heads-up displays, smaller, more powerful, thinner. It's critically important to manage the heat to improve the reliability of those devices too.
Okay, we have a question here. Why is siloxane problematic in gap pads?
Yeah, that comes up quite often in some of the discussions that I have, and thanks for that question. I typically just say that, like we did in the confined space of a cockpit, that siloxane is leaving the product and can build up on surrounding components or electronics. Having a hazy film or something that would be on a heads-up display could definitely impact the a pilot's ability to navigate and drive something like that, as important as a plane. I have one of my product developers on the line here with me too, who has a great chemistry background too, and Jeremy Higgins. Would you like to add a comment or two, Jeremy, regarding that siloxane? Because that is something that comes up quite often.
Sure thing. Joe, I hope you can hear me well here. So just a quick
yes,
comment on my side. Yeah, the siloxane issue with regards to thermal gap pads, just not to denigrate silicones. I mean, we sell silicone pads and they're great products. Siloxanes are the base material that you make the silicone pads out of. They also serve a sort of plasticizing role if there's residual monomers, and it's really this residual material that's problematic, particularly in confined spaces where you might have some thermal cycling. The volatilization and then condensing on surfaces can be problematic. Let's say if it happens on screens, as were mentioned on the talk, or in some of my other examples I've seen is when it deposits onto electromechanical devices, switches or relays. This is when the electrical systems start to behave badly. Acrylic systems don't have exactly the same problem. While there are some outgassing compounds, they don't do the same sort of deposition issues that can happen with siloxane.
Hey, Jeremy, thank you for that.
Yes, thank you. Next, we have a question. Do you have a product that is similar to graphite with very good XY conduction, but not so good in the Z direction for heat spreader applications?
Yes, thank you for that question. We do have thermal heat spreaders. We've developed a product line called, it's our product 9876 that is basically a electrically insulated heat spreader. It has a pressure-sensitive adhesive and die-cuttable liner on the opposite side, and it's used in those applications for small confined spaces, but you want to take the heat and move it very quickly in that XY plane to dissipate. Our 9876 product line has a thermal conductivity of 200 watts per meter Kelvin in that same XY plane. Okay, thanks for that question.
Okay, great. Our next question is the acrylic material a premium cost-wise or over the silicone material?
Oh, thank you for that. Yeah, as you know, 3M is a tape company, and many of our tapes that we produce are based on acrylic chemistry. As such, what we're finding is that we've got acrylic gap pad and acrylic thermal tape solutions that are delivering the performance design engineers are after, but at a price that is generally, the acrylics are less expensive than the silicone, or our silicone options. There's another advantage, though, to that, too, and we talked about it earlier, and it really was about assembly. If we step back and take a moment to talk about how will this final assembly be put together, another cost savings that comes into play is our acrylic portfolio, is even our gap pads are rotary convertible. So we have long length rolls of gap pads that can be rotary converted into indexed parts. Converter partners add secondary liners all the time with alignment holes or peel tabs, and as such, they address those assembly costs by making it easier at the tier supplier. So, yeah, it's a great question. Thank you.
All right. Next up, we have what is the status of graphene carbon nanotube phase change material solutions? Does 3M offer these?
No. And we may have product development going on, but I'm not familiar with that still. Thanks.
Okay, well, I think that we are going to wrap up the questions there. Thank you again, Joseph, for taking the time to talk to us today. If we weren't able to get to your question live, don't worry. All of the questions submitted will be posted on our website along with the answers. Watch for an email from us within the next 24 hours. We'll be sending you a link to the on-demand version of this presentation. In just a few minutes, we'll be starting our final session of this year's Thermal Live, so you don't want to miss it. Join us as we close out the event with thermal analysis, electronics reliability, and the influences of variability. Once again, I'm Jennifer Arroyo with Electronics Cooling. Thank you for joining us at Thermal Live.